working now? Yeah. Okay. Thanks for the introduction, and thanks for the invitation to come back to Kobe and to present to you at the symposium here. I was here 2 years ago, and it's very nice to be back. We've been collaborating in the Scalasca project with Riken for just over 2 years now, and so I'll talk about Scalasca collaborations a little bit more generally, but focus specifically on the collaborations we have done with K-Computer with Riken. I'll talk about collaborations in several areas in the development of the Scalaska toolset, some collaboration we had with Itaru Kitayama using Scalaska on the K-Computer, and then finalize with some collaborative training that we're also doing in the context of the VIHPS, the Virtual Institute for High Productivity Supercomputing. So Scalaska is a toolset that was developed specifically for scalable performance analysis of very large-scale parallel applications, the sorts of applications that are running on K-Computer, that run on our Blue Gene system, the Ukraine system, or large Cray systems, the Stampede cluster, etc., Tianhe, the system in China. These applications have very large numbers of MPI processes and threads, either OpenMP or POSIX threads, and typically are a hybrid combination of those. And we've tested our tools up to 1.5 million, 1.75 million threads, or over 1 million MPI processes. The toolset supports runtime summary profiling and also parallel event trace analysis at those scales. It's available as open source, and if there's interest, there's more information available from our website. The idea for our parallel trace analysis comes from the notion that it's straightforward to tell how long, for example, an application is spending in MPI operations. So here we have MPI sends and receives, for example. But it's much more difficult to actually work out that in this case, the receive is started early and the receive has blocked for some period of time before the corresponding send has been initiated. We can't tell exactly when the send takes place within MPI, but it certainly can't start before you initiate the send from the application level. So as an approximation of how much waiting time there is on the receiver here, which we call late sender in this scenario, we can compare the information we have about events on the two different processes, compare the starting times, and then report this as late sender time for the receiver process. That's a relatively simple example, but there's more complicated examples here where there's a couple of receive operations, and depending on the order in which the two events are received, there's different amounts of waiting time. Or if it's a collective operation, the collective operation typically can't proceed until the last of the participating processes participates in the collective operation, such as an all reduce or an all-to-all operation here. If it's an operation with a root, such as a broadcast operation, it's not all of the processes, but the ones which are initiated before the corresponding root process starts the broadcast. So these are the sorts of inefficiency patterns that we can look for in our Scalaska trace analysis and report those waiting times as a proportion of the corresponding times in the MPI operations itself. And while there's relatively little you can do to improve the efficiency of MPI itself, assuming that the implementation is relatively well optimized, you can avoid these waiting times by avoiding load imbalance issues, by posting sends so that they're done asynchronously and they're available for the corresponding receive. So these are things that application developers can work on. We also have recently added support for critical path analysis. So again, we can compare the events happening on different processes. We can work out which are on the critical path. The critical path connects point-to-point communication events or collective communication events. And by working through these events, we can actually work out which events are on the critical path, and only the events on the critical path are the ones which would actually benefit your overall application running time. If you reduce the time of something that's not on the critical path, you'll just end up with more waiting time somewhere else. So those are the sorts of metrics that we can get. It's possible to look through the traces manually to find these events with a trace visualization tool, but there are many of these in the applications, and they're often hard to spot. Whereas our automatic search can do this much more efficiently. It can go through very large amounts of low-level event trace data and distill it down to something that's a much more compact and much more valuable high-level result. And then we'll present this information in our three-dimensional display, where we look at the different performance properties, the different metrics that we can calculate, and associate these with different program locations, the processes and threads, and which execution paths of the application these metrics apply to. And by doing it automatically, we're guaranteed to cover the entire event trace. It's typically much more efficient and much faster than a visual inspection. And by using the power of the parallel computer itself to do the analysis, by replaying the events, we're able to use the available memory and the available processors and make sure that the trace analysis is typically as scalable as the application execution itself. Scalasca started in 2006, so we're almost at our 10-year anniversary. It was based on a preceding project called Kojak that started some years before that. That was doing the same sort of analysis, but used a serial form of the trace analysis, and that had very limited scalability. We quickly reached that with our Blue Gene systems and needed a scalable alternative. We've collaborated over the years with the University of Tennessee, Knoxville. Our colleague Felix Wolf was based there at the time, and then he moved back to Germany, and he's now at the Technical University in Darmstadt. The work on the K-computer was done here by Tomitake Nakamura when he was working here at RIKEN AICS, and he did the initial support for the K-computer, also extended that support for the Fujitsu systems, FX10, FX100, so we're very grateful to that support that we got there. We are also given access to K-computer so that we can continue to support the system and develop the tools further. The initial version of Scalasca had its own internal measurement system. We're now using a second generation of Scalasca, which is using a community-developed instrumentation and measurement infrastructure called Scorpio. This is developed by us in collaboration with a number of partners, the Technical University of Darmstadt, Dresden and Munich in Germany, the local Technical University in Aachen, as well as the University of Oregon, and one of the local companies in Germany was a partner in this development. In addition to these partners who are working very closely together, we continue to get support from Tomitake Nakamura now that he's back at Fujitsu Limited, providing support for us and contributions to support not only K-computer but also Fujitsu platforms more generally. Scorpio has support not just for Scalasca but also for a number of other parallel performance analysis tools. So Scalasca is here up in the top left. Vampire is a trace visualization and trace analysis tool that uses the same event traces as we use for Scalasca coming from the Scorpio measurement infrastructure. Tau is also using the call path profiles in cube format or an internal Tau format. And there's an additional tool from Jülich called Periscope that is more looking at the online interface, using an online analysis of measurements rather than these post-mortem measurements and analysis. The Scorpio measurement infrastructure has a number of different components to it that manage the measurement and store the measurements at the end of execution, and it has a number of different what we call adapters to interface to the MPI libraries, to OpenMP and POSIX threads, to accelerators if those are available and used on the systems, and there's also additional interfaces here for user instrumentation or for instrumenting source code more automatically, such as for OpenMP. Scorpio is used in the Scalasca workflow as the instrumentation and measurement part, so we instrument the application sources and link in our measurement libraries to get an instrumented executable. That instrumented executable, when it runs in parallel on the parallel system, and then at the end of measurement we have a couple of options. We can either write a summary report, which will then be presented in our analysis report explorer called Cube here. I'll show you a more clearer example later. Typically, we would take that initial measurement report, we would do some analysis of it, we would do some scoring of it to figure out what it contains and what value there is in that report. We're particularly interested in the communication and synchronization operations, so anything that doesn't directly relate to those is often something that's superfluous and can be filtered out. And that's one way of customizing subsequent measurements to remove extraneous information or potentially add additional hardware counter measurements and get a more refined and more a richer report for presentation. That initial stage allows us also to determine how much memory we would need, how large the execution traces would be, so that when we want to do a trace collection and analysis. We would then reconfigure the measurement system. We don't need to rebuild and re-instrument the executable. We can use the same instrumented executable, but we would just rerun things and then say this time we want parallel traces to be written, and then as a post-processing step, those execution traces would be analyzed in parallel with the same configuration, so the same number of processes and threads as the execution configuration for the trace analysis, and then distill that down again into an augmented weight state analysis report that then would be presented in the same sort of form as we see here from the summary reports. So that's the general workflow. I've just reported it again there. So how have we used Scalasca on K-Computer? I'll show you now a couple of application examples. This is work that was done by Itaro Kitayama here at RIKEN. The first example that he was looking at was a genome sequence assembler called Abbess. This is operating in a number of different execution steps or stages, which they refer to. So it loads in the sequence data, it breaks things up and distributes it across the processes. It's looking for overlaps, it's doing some quality control to remove errors and parts which are incomplete, and then it assembles all of these sequences that it has determined together into large contiguous sequences. The part that we were interested in is using MPI. It's running in parallel, running on C++, and it's using a master-worker parallelization. So the master directs what the different processes are doing. It takes them through the different stages here, and at the end of each stage, they report back before they continue to the next stage. The initial measurements on K-Computer were somewhat disappointing. They showed that it scaled quite well up to about 1,000 compute nodes, and then the performance quickly deteriorated. Not only did the execution time deteriorate, but the amount of memory that was required for the application was growing, in this case, linearly. So that beyond about 8,000 nodes, we had exhausted the available memory on the K-Computer compute nodes. So that was a secondary limitation that was disappointing and affecting us. So this was part of the motivation for us to look at the execution with Scalasca and try and work out if we could improve things here. This is one of the first measurements that we did with Scalasca. So we just did our normal approach of instrument everything and see what's in the measurements that we got. This was quite challenging because it's a large, complicated code that has lots of C++. So the methods here, the method names are quite long, and the whole call path structure was very complex and challenging to interpret. But at least in the Scalasca measurements, we can quickly identify the proportion of time that's used for communication. In this case, it's actually not so significant, but we can identify where how much communication there is and which parts of the application execution are taking significant amounts of time, and then investigate further. So we have the metrics on the left-hand side. We have the different call paths in our tree here in the middle pane, and then we can look at the distribution of how the values vary across processes here on the right-hand side to identify load imbalances and work out where inefficiencies are occurring. This first view here is from the sort of metrics that we get from the summary measurement analysis. The second picture here is going beyond that. We now have additional metrics that we can determine from the parallel trace analysis, looking at the different inefficiencies in the communication here. What's highlighted in this case is the time for collective operations, waiting at collective operations before those can actually take place on the K-Computer. And it's identified the most severe instance of that pattern. So here we're looking at an MPI all reduce. We're looking at the time that's waiting before the last process participates in the all reduce operation. We look at all of those instances, aggregate them together to show them in the call path profile here. But we also keep statistics that allow us to determine what the most severe instance of this pattern is. And you probably can't see it on the numbers here, but it's telling us that there's at least one instance of a process waiting for over 2 seconds in an all-reduced operation for the corresponding partner processes to participate. And that's a single MPI all-reduced call, not the aggregate in this case. It was relatively hard to figure out what was going on here because although we could see there was lots of inefficiency, the load imbalance didn't actually look so bad. The rank 0 stands out. It's doing different things. So it, of course, has much more waiting time. It's not participating in the computational part. But all of the other processes actually looked fairly well balanced, and so it was hard to spot and work out where the inefficiency was coming from. To get a little bit more insight, we would then look at things with a trace visualization tool like Vampire. Here we're actually seeing a timeline, so we have the 300 seconds of execution, 5 minutes of execution on the horizontal scale here. Here we have the different MPI processes on the vertical scale, and it's relatively easy to spot that there's a phase at the beginning here where there's loading the sequence data and redistributing it between the processes. We see there's a kind of wave pattern here where they load up their internal buffers, and then when those get full enough, then they start exchanging them, transferring them to the corresponding other processes. And then there's also some different behavior that shows up later on. The part at the end is the assembly part. That's actually the most inefficient part. There's a lot of waiting time here, but we can also identify a phase here, which is the erosion phase, which is a sequence of all reduce operations. And one of these all reduce operations, one of them in here, on rank 271, is the one that was highlighted as taking more than 2 seconds for that specific all reduce. But we can actually see from this picture that there's some variation, of course, but it's actually from high ranks to low ranks, it's diminishing and increasing in alternating phases. So there's alternating phases here with the all reduces where they do some computation, more on some processes and less on others, and then it's reversed for the second one. And the result is that more than half of the time is actually wasted with processes waiting for their partners to get ready to continue. So this was interesting for us. We learned a lot about the execution of Abbess on the K computer. It was a complex, challenging application to work with, but we got some insight into what was going on. We found that the communication was increasingly expensive. Load balancing was increasingly breaking down and becoming less efficient at larger scale. So those are things that we thought we might be able to look at improving. We also noticed, not just from the Scalasca measurements, but more generally, that execution time was varying significantly from run to run. And we were not able to say definitely at that point, but our suspicion was that this was file I/O, both for loading in the original data from file, but also writing out the sequences in the course of the simulation of Abbess. But we also noticed that the default instrumentation we were doing of instrumenting everything was prohibitively expensive, so our runtimes were dilated very substantially. It was very difficult to filter things down to something more manageable due to the code structure, partially because of what's happening and the runtime-driven nature of the simulation. It was difficult to correlate what the master was doing with the workers that it was directing, and that made it difficult to distinguish these important execution stages. And we also didn't get information about the file I/O. So these were all things that we thought we could work on improving. Our next stage was therefore to revise our strategy. We removed the compiler instrumentation and did manual instrumentation. So we manually went into the code, annotated the important phases ourselves. We also annotated the file I/O operations so we could see those in our analysis. And that substantially reduced our measurement overheads. They essentially became negligible at that point. If we were to collect everything, the traces would still be huge, but we could focus down and just look at specific phases of execution rather than actually trace the entire execution when we were interested in that. So this was our second stage. That meant that our analyses became much simpler and easier to interpret. Here we can actually see the cyan color here, the light blue, is waiting time, and only the processes, each of the processes in turn does some computation here in one of the quality control phases here. So the master process directs each one in turn to open a file, to do some work, to calculate something, and then write the contents to that file, close it, and then start the next process. This, of course, is clearly non-scalable and inefficient. Not only is the file writing serialized, but there's no opportunity to exploit what the other processes could be doing at the same time. So there were a few things that we could, that was just one example of the things that we spotted in our revised traces, a number of other things that we could improve. The key thing that helped us to improve performance on K computer is to use the rank local directories for file I/O rather than the shared file directory. which was subject to a lot of file system contention, potentially from what the Abbess application itself was doing, but we also suspect there was a lot of file system contention from other processes running on K-Computer at the same time. We could, for example, in that previous example, we could create the files in parallel in advance of having to write to them. That avoided some of the serialization cost. It didn't remove all of the serialization cost, but it removed one of the most expensive parts of it. It also substantially reduced the disruption that we saw in the analysis in that stage and in the subsequent stage. The other thing that we did was that the application was doing a lot of point-to-point communication between the master and the other processes. This was one of the reasons for the linearly growing MPI requirements and the bottleneck for rank 0. By using collective operations, some of which are optimized for K-Computer, we could reduce the memory requirements and also have an improvement in performance as well. So here we're looking at two profiles, left and right as the original and the improved version, showing the different phases of the application execution. The one on the left shows this pop bubbles and discover bubbles as showing up as the most expensive operations. Those are then substantially reduced in cost. So instead of taking over 70% of the execution time, they were reduced to just 4 or 5%. Here we've gone up to about 8,000 processes at a larger scale. There's still a substantial bottleneck in the assembly that is still remaining that would need further work, but we've had a substantial improvement there as well, and there's also a reduction in the time as part of loading in the initial data as well. So this was all very positive. It allowed us to get a substantially better improvement here. It still hasn't given us all of the benefit we would like, because we didn't completely finish this parallelization, but we were able to, on the one hand, reduce the memory requirements from these yellow bars down to the orange ones, so they're now much more manageable, essentially negligible. That allows us to run the program at larger scale. We only did the collective transformations for the loading phase and verified those, the benefit of those. So the red line going down to the green line. There'd be a lot more work to apply similar transformations for the remaining phases of the application, but that was already a positive start. So just to review how far we got with Abbess before deciding that basically this application isn't one that's going to scale well on K-Computer or similar systems. There's inherent problems in the file I/O. There's inherent bottlenecks that are just beyond our control to rectify here. But we're able to use our tools, Scalasca and related tools, to identify and quantify the inefficiencies and be able to figure out which ones we needed to resolve. And at the end, we were able to do a measurement of the Abbess application with Scalasca on the full K-Computer up to the 82,000 compute nodes. Even if it was just the initial phases of the execution, we did a measurement right up to the full system. I want to move on and tie into our previous talk on the Nest simulation tool. So this is what Itaro is now working on. This is a C++ simulation using MPI and OpenMP, so it's a little bit more interesting and much more scalable. And there's two different experiments that we've done. Itaro has been working on the K-Computer, and we were looking at the performance there, so I'll show you a couple of screenshots there first. Here, this was run on the full compute nodes of the K-Computer. So we have over 650,000 threads of execution here. What I've highlighted is the time in the gathering events part. So after a simulation phase has been done, there's some gathering of events and exchange of information between the processes with the corresponding synapses, exchanging information before the next simulation step. Here we can see that it's taking around 53 seconds of execution here. This is a master region, so it's only executed on one of the 8 threads on the K-Computer node, and that's where the communication is done to do this exchange of information. And then there's a barrier synchronization afterwards. So it's no surprise that things are well balanced, but actually what we see if we just look at what's happening inside the region is that there's quite a variation here between the processes. Some spend very little time, a number of them, or some of them spend over 50 seconds, and then this is the median time down here of 6.5 seconds. So there's a considerable load imbalance across the MPI processes here for that exchange. Part of the challenge that we're discovering is it's difficult to understand the variation between the threads within each compute node, and then also correlate that to imbalances across the compute nodes between the MPI processes. This is a second example. It's not actually from K-Computer, but from our BlueGene-Q system. It's a different configuration of Nest where, again, it's running on our complete BlueGene system, in this case 450,000 threads of execution here, or cores. And we're looking at how to load in the initial configuration data, the initial connectivity information for the brain simulation. Here again, we're seeing it's taking a couple of minutes to load the data. I think it was close to 2 terabytes of data that was being loaded in this scenario here. Again, it looks fairly well balanced by the time you get to the all-to-all exchange of information after reading in the data. The all-to-all itself shows that there's a significant variation across the processes, and the origin of that variation is the fact that the reading in the data itself varies from 1 second up to 86 seconds. So the reading in of the data by the different processes is varying substantially, and what we were able to spot here is that this is an individual file operation. It's using MPI file I/O through HDF5. Although the application was using a collective HDF5 read operation, internally we can see it's not using a collective file read, it's using an individual file read, and that's one of the reasons why there's so much variation here. It's also one of the reasons why it's not very efficient. So they were able to spot this, and they're now in the process of converting this to actually use a collective operation. The reason that HDF5 was substituting individual file operations was that there was some data structure mismatches between the HDF5 data structures and the data structures that they were reading the data into. So that's something that they're working on resolving right now. This measurement was done in the context of an extreme scaling workshop that we had at the beginning of this month in Jülich. We've had a number of these workshops over the years on our BlueGene systems. It's an opportunity to run applications on the full system for a dedicated period of time. We had the machine reserved for 50 hours, and we had 8 international code teams participating in this workshop. The results will appear in a report once we have that finished at the end of this month, perhaps when I get back to Germany. But we have a number of applications that have already passed through such workshops, or more generally demonstrated that they can scale and execute on the full UQueen system. So we have examples of 25 members are currently proven that they have been able to meet this challenge, to be able to scale up. Either they use 1.75 million MPI processes. That's very restrictive in terms of the amount of memory per process. So often you're using a combination of MPI or an OpenMP, and then scaling up to use the entire UQueen system that way. We have published this information in terms of the HiQ Club, which is on our website. Last year, we also organized a couple of workshops. We were also able to take the opportunity to invite colleagues here from Riken and Tokyo Tech and other institutions to come and share their experience. And we found that very valuable to see how things compare on K-Computer with Sequoia, with Stampede, Shanghai, etc. So those are, you can Google for those and find those websites. You find the presentations there. The proceedings from the Maxi workshop should appear in a couple of weeks, I guess. I don't want to spend time going through the analysis, but basically we're looking at the scalability of the code, how it scales up to the full 28 racks, the full 450,000 cores. The top scale here is the strong scaling results. Some codes are more looking at weak scaling. We're fairly flexible. If you show some benefit at larger scale, then you meet the requirements for membership of the club. We're comparing the parallelizations that they're used, what the languages they're used. Everything looks pretty standard as far as we see. Most people are using MPI and often in combination with OpenMP. And then they're mixing and matching how many processes, how many threads, but typically using all of the hardware threads that are available on the BlueGene-Q system. So 64 threads or 64 processes per node in total. I've only a couple of minutes left, so finalized here with our training activities here. Scalasca training is done through the Virtual Institute for High Productivity Supercomputing. There's another website here for you to look at. The focus is on parallel performance, correctness, and debugging tools. We organize several VI-HPS tuning workshops each year. These are typically 3 to 5 day events where application developers come along. They get a chance to try out the tools, receive guidance on how to use them, and assistance applying these tools to their own codes. We did a workshop here at Recon 2 years ago. We're very happy to be back and doing a workshop immediately following this event. That will be an opportunity for people to try out tools on K-Computer or the local Fujitsu FX10 system using Scorpio, Scalasca, Tau, or the Barcelona tools. There'll be additional workshops later this year, one coming up in Garching in Germany, and then another one in June in Montpellier in France. So there's a whole range of workshops. We're always looking for new opportunities to do these workshops. We did a workshop last year in Santiago de Chile. That was our first workshop in the Americas, our first workshop in the Southern Hemisphere, also our first workshop where we didn't do in English, but which we did in Spanish. And these are all the different partners that are part of the Virtual Institute, many of which are also present here. I don't have time to talk about all of the tools that we have in the Virtual Institute. Some of the names I hope you recognize, some of them you might not, but there are a whole range of debugging and correctness checking tools here, profiling tools, and tracing and trace analysis tools. We have a tools guide that you can download from our website, and that will give you information about the capabilities of the different tools and which platforms they support, etc. So I hope that there's a lot of information there for you. Thank you.